Section 250.52 A6 addresses ground rod length. It specifies that 3/4-inch minimum diameter rods and pipes of any material shall be used. However, Exception 1 states that 5/8-inch diameter ground rods of galvanized steel at least 6 feet in length shall be permitted. Section 250.52 A7 discusses maximum resistance. Driven rods or pipe shall not be less than 8 feet in length where the electrode resistance to ground is more than 25 ohms. Where rod or pipe electrodes 25 feet in length cannot be driven, ground ring electrodes complying with 250.52 AH shall be installed. Therefore, according to the NEC, 5/8-inch by 8-foot galvanized ground rods are permitted. An authority having jurisdiction, or AHJ, may have their own reasons for insisting on copper-clad ground rods. This decision could be based on local soil conditions or past experiences. It is important to understand the role of the AHJ in enforcing electrical codes. While the NEC provides a baseline for electrical safety, local AHJ have the authority to implement stricter regulations based on their specific needs and circumstances. Even if the NEC permits the use of galvanized ground rods, the AHJ can still require copper-clad rods if they deem it necessary. It is crucial to comply with the AHJ requirements in such cases. This is because the AHJ has the ultimate responsibility for ensuring electrical safety within their jurisdiction. The NEC is not a law in itself. It is a set of guidelines that are adopted and enforced by local governments. The AHJ plays a vital role in adapting and interpreting the NEC to fit the specific needs of their community. When there is a conflict between the NEC and the AHJ requirements, it is essential to prioritize the AHJ regulations. They have the authority to make decisions that supersede the NEC in their jurisdiction. This authority is granted to them to ensure the highest level of safety for the public. The AHJ decision to require copper-clad ground rods may be based on several factors. Firstly, copper is a highly conductive material which can provide better grounding performance in certain soil conditions. Secondly, copper is more resistant to corrosion than galvanized steel, which can extend the lifespan of the ground rod. Thirdly, the AHJ may have observed a higher failure rate of galvanized ground rods in their area due to specific environmental factors. It is important to communicate with the AHJ to understand their reasoning for requiring copper-clad ground rods. By understanding their concerns, you can work together to find a solution that meets both the NEC requirements and the AHJ regulations. In some cases, it may be possible to provide data or documentation to support the use of galvanized ground rods. This data could include soil resistivity measurements or test results demonstrating the effectiveness of galvanized ground rods in your specific location. However, ultimately, the decision rests with the AHJ. If they remain firm in their requirement for copper-clad ground rods, it is essential to comply with their decision to avoid potential safety hazards and code violations. Remember that electrical codes and regulations are in place to protect people and property from electrical hazards. While it is important to understand the NEC requirements, it is equally important to respect the authority of the AHJ and comply with their local regulations. By working together, electricians, inspectors, and AHJ can ensure the highest level of electrical safety in every community. Consider also that the exception permitting 5/8-inch galvanized ground rods specifies a minimum length of 6 feet. While an 8-foot rod meets this requirement, it's important to note the specific wording of the exception. This exception exists to provide some flexibility in situations where larger diameter rods might be difficult to install, but it still maintains a minimum performance standard by requiring a certain length of the galvanized rod. It is also worth noting that the 25 ohms resistance to ground requirement mentioned in section 250.52 A7 is a crucial factor in determining the effectiveness of a grounding system. If a single ground rod does not achieve a resistance of 25 ohms or less, then additional ground rods must be installed. These rods must be placed at least 6 feet apart to ensure proper performance. The purpose of a grounding system is to provide a low impedance path for fault current to return to the source. This allows the overcurrent protection devices, such as circuit breakers or fuses, to quickly trip and energize the circuit in the event of a ground fault. A properly installed grounding system is essential for preventing electrical shock hazards and minimizing the risk of fire. It is also important to consider the type of soil in which the ground rod is being installed. Soil resistivity can vary significantly depending on the type of soil, moisture content, and temperature. High soil resistivity can make it difficult to achieve a low resistance to ground. In such cases, it may be necessary to use multiple ground rods or other grounding methods, such as ground plates or ground rings. Ground rings are a continuous loop of bare copper conductor that is buried in the earth. They provide a very effective grounding system, especially in areas with high soil resistivity. Ground plates are another option for grounding in difficult soil conditions. They are typically made of copper or galvanized steel and are buried vertically in the earth. In addition to the NEC and local AHJ regulations, it is also important to follow the manufacturer's instructions for installing ground rods. The manufacturer's instructions may provide specific recommendations for spacing, depth, and connection methods. Proper installation is crucial for ensuring the long-term performance and reliability of the grounding system. When connecting the grounding electrode conductor to the ground rod, it is important to use a listed connector. A listed connector is one that has been tested and certified by a recognized testing laboratory such as Underwriters Laboratories or Intertek. Listed connectors are designed to provide a reliable and corrosion-resistant connection between the grounding electrode conductor and the ground rod. The grounding electrode conductor must be sized according to NEC Table 250.66. The size of the grounding electrode conductor is based on the size of the service entrance conductors. It is important to use the correct size grounding electrode conductor to ensure that it can safely carry the maximum fault current. The grounding electrode conductor must be installed in a continuous length, without any splices or joints. This is to ensure that there is a lower impedance path for fault current to flow back to the source. The grounding electrode conductor must be protected from physical damage. It can be run in conduit or other approved raceway to provide protection from impact or abrasion. In addition to the grounding electrode system, there is also a bonding system. The bonding system is designed to connect all of the non-current carrying metal parts of the electrical system together. This includes metal conduits, metal enclosures, and metal equipment. The purpose of the bonding system is to create an equipotential plane. This means that all of the metal parts are at the same voltage potential. This helps to prevent electrical shock hazards by ensuring that there is no voltage difference between the metal parts. The bonding system must be installed in accordance with NEC Section 250.92. The bonding jumpers must be sized according to NEC Table 250.102. The bonding jumpers must be installed in a manner that provides a low impedance path for fault current to flow. The bonding jumpers must be protected from physical damage. In addition to the grounding and bonding systems, there is also a surge protection system. The surge protection system is designed to protect electrical equipment from voltage surges. Voltage surges can be caused by lightning strikes, utility switching, or other electrical disturbances. Surge protection devices, or SPDs, are installed at the service entrance and at sensitive equipment locations. SPD work by diverting the surge current to ground, protecting the equipment from damage. SPD must be installed in accordance with NEC Section 285. The SPD must be sized according to the voltage and current requirements of the equipment being protected. The SPD must be properly grounded and bonded. The grounding and bonding systems are essential for the proper operation of the surge protection system. A properly installed grounding and bonding system provides a low impedance path for the surge current to flow to ground. In summary, the use of 5/8 inch by 8 foot galvanized ground rods is permitted by the NEC under certain conditions. However, the local AHJ has the authority to require copper-clad ground rods if they deem it necessary. It is important to communicate with the AHJ to understand their reasoning and to comply with their local regulations. A properly installed grounding system is essential for electrical safety and should be installed in accordance with the NEC and local AHJ regulations. Remember to always consult with a qualified electrician for any electrical work. Electrical work can be dangerous and should only be performed by trained professionals. They can assess your specific needs and ensure that the electrical system is installed safely and in accordance with all applicable codes and regulations.